Hello, everybody. Welcome back. In this lesson, we will go over a few different extensions of the concept of limit. Now, to understand these extensions, we need to understand the meaning of limits in terms of its notation. First of all, in terms of the topics or the agenda of this lesson will be understanding infinite limits and limits at infinity. So try to understand the difference between these two, at least in terms of like the verbal difference between these two phrases, infinite limits and limits at infinity. Now, let me show you the difference between these two concepts in terms of the notation that we considered, right? Recall the notation. So when it comes to the notation of limits, what we had was, first of all, verbally, the way that we convert this particular mathematical statement to regular wording is basically limit of function f of x as x goes to a equals L. So that is the statement. Now, if you look at this expression, you can see a couple of things. This is exactly the output or the outcome or the value, the final value of this computation. And then when you consider this value A, that tells you exactly at which point, where it occurs. So here it says where, and this is the outcome. More precisely, I can say what, that quantity that we're looking at. So where and what. So those are the two uh, pieces that we're going to look at. Now, when it comes to the first variation, we will consider this kind of a situation where we are going to have this kind of a symbol, limit x goes to a something, and here in this case we will be precise with either one side, like from the right side or the left side. But when you consider the function, now we will get an output in terms of an infinity. So what, or in other words, the value that you're going to end up getting is an infinity. Now this kind of a scenario is called an infinite limit. Infinite limit, because the limiting value itself becomes an infinite value. It is not a particular value, instead it is a never ending process, so it is infinite limit. On the other hand, when we consider putting infinity in the place of a, other than having a right here, if we replace that value by an infinity, and yet you can talk about this, and yet here you can end up getting a certain value yet. But now in this case, you can see the significance. Now, other than having a value, a finite value a, we are going to have just infinity included here. So this kind of a situation is called limit at infinity. So now, as a summary, to understand this nature, you can simply have two placeholders in this picture. Limit as x goes to a blank f of x equals a blank. Now, when it comes to an infinite limit, you're going to fill this block with an infinity. It could be either positive infinity or negative infinity. And when it comes to limit at infinity, you're going to fill this block by an infinity. It could yet be again positive infinity or negative infinity. The meaning of infinity is simply it is a never ending process. It is not a value. Instead, we are going to call it a never ending process. So now, provided that we have an idea about what we are going to deal with, the variation of two main components that we are going to deal with in this lesson, Let's look at the tools that we are going to use or employ in this scenario. It is super straightforward equation that I can provide you qualitatively other than providing a quantitative representation. Look at this. If I divide 1 or any constant, any non-zero value by a very large number, if I divide 1 by a large or a big number, the outcome that I'm going to get is very small. If you do not see this, think about a numerical example, like let's say 1 divided by 10,000, or like let's say 1,000. 1,000 is not that big, but yet let's say when you consider that, you can see the value is going to be 0.001. When this value is increased, the outcome that you're going to get is small. Now, when you have that particular tool, you can just flip the same tool the other way around, and you can say, why not? When we have 1 over, let's employ a different color, 1 over a very small number will result in a very big outcome. So this simple quantification is all you need to have in these limit computations. And first of all, even before starting this session, in terms of computations, let me tell you, the computations are going to be straightforward. In most cases, you're going to get direct, like let's say it's just like multiple choice kind of solutions that you're going to get, either one option or the other. The computations are minimal when you understand the role of this tool in your computations. So to make it more precise, now I would call it, now this is not the best representation, and let's make it more mathematical. Before leaving this simple tool, I will make it like this. When x goes to infinity, if I put 1 over x, now this simply means I'm putting a very large number in the position of x, and I consider 1 over x. Now, since for large denominators, I'm going to get small outcome when x goes to infinity without having a bound. When it increases, there is no option, it's going to be just 0. So once you have this observation, you can just have plenty of varieties of that. You can just have x square, you can have x cubed, or even accompany that by, like, let's say different constant here, negative 13, other than having 1. It doesn't really make any difference, because as far as you have a constant, non-zero constant at the top, together with a value that's increasing without having a bound, you're going to get just 0. And on the other hand, if you consider the other version of this story, if you consider when x goes to 0, right? When x is getting smaller, that means x is getting around 0. I would name one side, right? So one, okay, x is approaching 0 from the right hand side. In that situation, if you consider 1 divided by x, what's happening is you're working with this version of the story. So when the denominator is getting small, the outcome will be large. How large would it be? Since this is a process that never ends, it's always approaching 0 from the right side, this will result infinitely large number, and it will result a positive infinity. The potential variations that you can have in this scenario would be, let's say, other than having 0 from positive side, if you end up getting 0 from negative side, what you have is a number here which is essentially a negative value, because it's approaching 0 from the left side. So x itself is negative. If x is negative, the whole fraction becomes a positive divided by a negative, yet the value of the fraction is increasing infinitely with a negative sign now in front. So you can have that kind of a variation of that story. On the other hand, if you consider the situation like, let's say, yet this is going to positive 0 from the positive side, and if you have a negative 1 at the top, yet you have a negative fraction. A negative fraction, and the denominator is going to 0 where the numerator stays away from 0, so that will result again a negative infinity. So simply you can just make it, you can rotate it around, you can just alter it a little bit, get a slight variation of the story, but yet all of them are starting from one single origin, which I've written down right at the beginning. Let me put it in red color as I usually did at the beginning. These are the two tools that you're going to see in this story repeatedly in different contexts. And this is about limit at infinity. Can you see? Because x is heading towards infinity. And this one is the outcome. Outcome of the second expression is an infinity. Therefore, I will call it an infinite limit. Now, do you need to really think too much about how this would behave? No, nothing that you need to do in that way. Let's work with examples. Do you need to have separate theory for this situation? My recommendation, don't worry about having separate theory. It's just about practical approach towards these problems. Now look at this. Let me show you a couple of examples for infinite limits. That simply means what I'm going to get as an answer for this is going to be either positive infinity or negative infinity. So it is kind of like 50-50 chance. But we cannot have wild guess in the situation. We need to come up with a specific outcome, and it should be an educated guess, and not a guess at it should be educated, well educated computation. All right, so how can you do this? All you need to do is this. Now, when x approaches 1 from the right hand side, think about the variation of this component. X minus 1, so x is approaching from the right side, 1 is sitting right here, and x is sitting in the right side, and it's approaching from the right side. That is the meaning of this plus, superscript of plus, right? So when you consider this scenario geometrically, you can see x minus 1 is always going to be a positive value. Let's use a different color. So it's going to be a positive value, but at the same time, x is going to 1. So therefore, x minus 1, the difference between these two values will go to 0, and it's going to 0 as a positive value. So what happens to the denominator is a quantity that goes to 0 as a positive number. Let's analyze what's happening at the top in the meantime. When x goes to 1, even though you consider positive side or negative side, it doesn't really matter. In the numerator, plug in the value and see directly where it is heading. So when you plug in, you're going to get 3 minus 2 plus 1. So ultimately, it is going to be just 2, which itself is a positive number. Can you see? It is just a positive number. It is not a superscript of superscript is not meaningful in this occasion. What you need to understand is the parity, or like the sign of the number that you have, right? So it is none other than just 2. It's none other than a positive, right? So positive divided by a positive, we know that it's going to be a positive, and then we know the perfect recipe for an infinite limit output. That is the denominator going to 0, where the numerator stays away from 0. This is non-zero value, right? So once you have that simple recipe, all you need is this, your answer. So in this situation, you do not need a factorization or any specific simplification. All you need to understand is this perfect recipe that would prepare uh, the infinite limit output. So let's look at one more example. And even before going for an example, let's look at the graphical meaning of this particular scenario. What is the graphical meaning? Can you explain the graphical meaning of the situation? Now, graphically speaking, this is what we are seeing. I have no idea how this graph would look, how this function would look everywhere. But I do have an understanding exactly what would happen around 1 only from the positive side of this function, this graph. So when you consider the graph of y equals 3x square minus 2x plus 1 divided by x minus 1, it behaves exactly like this around. It's skyrocketing towards positive infinity when x values are approaching 1. So I have no clue how the function would behave afterwards. So it could be like a continuation like this, it could be continuation like that. We have no clue what kind of a mystery it's going to be. We have no clue what it's going to do in this half. But based on this limit computation, all we can say is this particular observation of an infinite limit. The function itself is going towards positive infinity when x goes to positive, when x goes to 1 from the positive side. And we will see this as a significance because in this scenario, we will call this kind of vertical line a vertical asymptote. Vertical asymptote. We will talk about that more in detail later. So vertical asymptote of this given function. So there could be more vertical asymptotes for a given function. The function could behave differently on the left and on the right side of a vertical asymptote. We will see that more in detail, especially when we get to the level of applications of differentiation. Now, let's look at the next example. Now, since we are already familiar with this concept, why don't we do this computation right away? X goes to 3 from negative side, left side. So that simply means this quantity is going to 0 as a negative number. That simply means the denominator is negative. In the meantime, the numerator goes to 3 square, that is 9, plus 2 times 3, that's going to be 15, right? When x goes to 3, either positive or negative side, it doesn't really matter in the analysis of the numerator. So it goes to positive 15. Therefore, what we have is positive divided by a negative. We know the sign now, it's a negative, and then an infinity, negative infinity. And the next example. Now, sometimes when we look at this kind of an example, now at this point, why don't you take a moment? Why don't you go ahead and pause the video for a moment and think about this and uh, to see if you can get the answer yourself. Think about it now. All right, I hope you gave a thought, right? So now let me explain. When x goes to 2 from positive side, we can see something now. The problem is in the denominator here, we can clearly see it's going to 0, but how can you decide from which side, the sign of it? It could be a little confusing. So in that kind of a situation, you can do something very easy. That means, of course, let's simplify it a little bit to understand the situation, what's happening in this. Let me just move it to the left a little bit so that we can have enough space. Now look at the denominator. This denominator has obvious factorization, x minus 2, x plus 2. Now look at this. If you look at these components individually, you do have your answer. When x goes to 2 from positive side or negative side, doesn't really matter. What happens to the numerator is it's going to negative 14. Just multiply negative 7 by 2. So it's a negative number. That's what matters. The number is not what matters. The sign is what matters. And when x goes to 2, x plus 2 goes to 2 plus 2. That is going to be just 4. And then in the meantime, when you consider this component, that is the mysterious component in this computation. And when x goes to 2 from positive side, this goes to 0 as a positive number. Now look at each and every component. What you have here is a division, and you have a negative divided by a positive and another positive. So what you have is a negative output and 0 in the denominator, or a quantity that goes to 0 in the numerator, makes the recipe for an infinity. Now, let's take a moment. Now, this is the answer. We're done with this second example. Now, if you think about division by 0, it is not something possible. It was not something allowed in algebra. But can you see how strong or how valuable the notion of limit that we introduce in calculus? Because even if you cannot define division by 0, you can have a meaningful interpretation based on a process for that situation. So that's exactly what we do by employing the concept of limit in this scenario. Let's look at the next example, and it is pretty much it is pretty similar, I guess. I guess you should have a couple of minutes to think about this, because it's not too complicated. Or I would say it is straightforward. Let's take a moment. All right, I hope you could figure it out. Now, let's try to see this. Now, when x goes to -1 from negative side, what matters in the numerator is where actually it's going. X goes to -1. So what happens is when you plug it in that value, you're going to get 5 minus 2 times minus 1. So it's going to be 5 plus 2 equals 7. So that is a positive value sitting at the top. And in the denominator, by any chance, if you do not like the way this looks, just have the factor x plus 1, 2 times x plus 1. 2 is a positive constant, and what happens with this one is when x goes to -1 from left side, this quantity is going to 0 from left side as a negative number. So now, if you come up with the final outcome, a positive divided by a negative, that would give you just a negative, and the perfect recipe, non-zero value divided by something approaching 0 in the denominator. So that prepares a recipe for an infinity. So now let's talk about the concept of vertical asymptotes. We talked about vertical asymptotes already. Just before getting to this, the vertical asymptotes are exactly this kind of behavior of a graph. When you have a graph, there could be a certain scenario, certain situation where the function is undefined at certain points. These undefined points could occur in a few different ways. One could be exactly these kind of infinite jumps where you have vertical asymptote. So now this kind of a situation is called a vertical asymptote. These two vertical red dotted line segments, those dotted lines are called vertical asymptotes. The function, where the function is approaching when the value of x is approaching a certain value from either side. So in other words, the function merge with these two vertical lines only at an infinite value. So it is the process that is exactly the identification of a vertical asymptote. So one nice way to identify vertical asymptotes would be the function being undefined. Function is undefined at both of these places. Can you see? But now when you say that, be careful, because undefined function appear in two different ways. One is this vertical asymptote scenario, the function is broken completely. The other situation is something like this, where you have a hole of the function. We already know the meaning of that kind of a situation, right? There could be a hole, or there could be even a situation like this, a finite jump, right? If you have a finite jump for a function, now in this occasion, actually, I drew it incorrectly. Why don't we have undefined value in both cases? Now, in this situation, you can see the function is yet undefined, but it is not an asymptote. It doesn't get infinity to merge this function with this vertical line segment. So there is no such behavior, right? Look at this. The relationship between the graph and this vertical line is they apparently meet at infinity. But here, there is no infinity in the picture. So when you try to identify vertical asymptotes, you need to recognize, you need to refine it from these possibilities. A hole or a finite jump would not be recognized as a vertical asymptote. Instead, these red vertical lines are going to be vertical asymptotes. And then, okay, look at this. This explanation could be like a little overwhelming because there are many moving parts, but the computations are super simple. Let me show you the first thing. To find vertical asymptotes, this is all you need to do. You need to look at the given function and you need to make sure that it is in the most simplified form. That simply means there are no unsimplified factors in the denominator. To check that, I will just factorize it, right? Now, when I factorize, look at this. Do we have this factor at the top somewhere in the numerator? No, the numerator doesn't have that kind of a factor. That simply means this cannot be simplified with the numerator. The same thing goes with this. So these two scenarios will inevitable, right? It will be inevitable possibility to have a vertical asymptote, or in other words, a function will achieve an infinite limit in either end, either positive infinity or negative infinity. So vertical asymptotes in this situation would be VA, I will write it in that form, VA would be these particular values that would make a 0 in the denominator. So when you set this one to 0, you're going to get x equals 2. That is one possibility. And then the other possibility would be when you set the other factor to 0, x equals negative 2. So the vertical asymptotes of the first graph f of x would be just these two unsimplified denominators. Now, since we have seen this, now why don't we work with the next example by keeping the same idea in our mind? Now, to analyze for vertical asymptotes, this is what we need to have. Don't forget, we need to have unsimplified zeros, or uh, zeros that cannot be simplified from the denominator. What do we mean by that? Let's try to simplify this. First of all, factorization matters in this case. So I'm going to do the factorization x minus 1, x minus 2. The whole thing is divided by x minus 1, x minus 2. Sorry, x minus 1 and then x plus 1 in the denominator. The top is factored and the bottom is factored. Can you recognize a common factor? Yes, there's a common factor in this scenario, right? X minus 1 is a common factor. Now look at this. If you blindly look at the zeros of the denominator and say like the vertical asymptotes are going to be x equals -1 and x equals 1 from this factor, your answer is incorrect. So this is not a possibility. The only possible vertical asymptote is coming from this factor which cannot be removed from the factorization. So it cannot be simplified with the numerator. So that is the way to recognize it. So it is very simple. To recognize vertical asymptotes, what we're going to do is to simplify the numerator and the denominator as far as we can, right? So let's try to do it right here also. Now, I made this one little complicated or little um, sophisticated, but if you see the factorization right away, you know what it is, right? Can you factor the top? If you do not recall it, think about it. That is factoring by. I'm going to give you 1 more minute. Or think about. All right, pause the video and think about. Do the simplification, and you can earn some confidence with that. All right, I hope you gave it a try. Now, with this, look at this. You can factor by grouping at the top. So you're going to get x squared from the first two, then x minus 1, and then plus. The second term is none other than just x minus 1. Now you can see the factorization of this. X minus 1 is right there. And then in the denominator, you have x minus 1 and x plus 2. That is the factorization. The top has two common factors yet. Factor it out, x minus 1, and then you have x squared, and then once you factor x minus 1 here, that would be plus 1. The whole thing is divided by x minus 1, x plus 2. When you cancel this, the only unsimplified denominator or the factor in the denominator would be x plus 2. So the vertical asymptote in this case, VA, will be x equals -2. Set this part to 0 and that value. Now, when we answer for vertical asymptotes, we always provide the answer as x equals a value. Do not say the vertical asymptote is -2, just -2. -2 is a number, but when you write it like x equals -2, that provides a geometric object. What kind of a geometric object is it? It's a vertical line on OXY plane. All right, so with that, now we get to the next half of the story, limits at infinity. Now we already saw the recipe or the tool. Now what we are going to do is to look at it, first of all, to get an intuition. Let's talk about this uh, graphically. Now what happens is what happens in this scenario is something like this. There could be certain values of a function where the function is actually reaching when x goes to infinity. So it is just like a horizontal line the function is getting aligned with. So this is the graph. Actually, I'm showing you. The graph is getting aligned, and we need not to have any clue about what's happening in between. It could be some behavior of this function, like going any any possible way. It could be like that. It could be something with a horizontal, vertical asymptote, something like that. So it could be any of those possibilities, but that is not the concern that we need to have in this scenario. Our consideration is exactly this behavior. The function is getting aligned with a horizontal line segment, and this line segment is called a horizontal asymptote. And the same thing with this one. For a certain function, there could be more horizontal asymptotes, like more than one single horizontal asymptote, or there could be a single horizontal asymptote. In most examples that we're going to see, related with um, just polynomial functions, we are going to see only one horizontal asymptote that you're going to see in the upcoming conversation. Now look at this. Now again, the tool, let's recall the tool, limit when x goes to infinity. So this is a limit at infinity. So when x goes to infinity, you're going to see a finite or infinite limit. So here the answers are not going to be just like 50-50. It is not like it has more spectrum because you can place these horizontal line segments at any height. It could be here, it could be there. There are many options, but understanding the computation is pretty simple. And this is the starting step, and that is the tool. And then the main tool that you're going to employ is when x goes to positive infinity, 1 over x is going to be 0. This would yet stand even if you have limit x goes to negative infinity, 1 over x, yet it's going to be 0. So nothing to worry about like any powers. You're going to get the same observation. So let's look at these examples and let me show you what to do in this kind of a scenario. Now, if you directly look at x going to infinity in this situation, x goes to infinity and you're trying to compute the limiting value of this. Don't forget, our toolbox has only two tools, something like this. Only minimal amount of tools, I would say. Now, in this situation, how can you employ what you see right here to answer something like this? Now, the problem here is if you try to have direct substitution, you're going to get when x goes to infinity, you're going to have an infinity here and then minus 5x, yet it would be an infinity. So you can say, you would say minus infinity. But once you have this, there is a huge uh, confusion or ambiguity. How can we compare infinities? Can you do that? Can you say like these are not numbers? So infinity minus infinity would not give you any sense. So we need to avoid it at all cost. And even if you get through that, if you do this, eventually you will end up getting infinity by infinity. That is not a meaningful representation of the answer because infinities are not numbers. Therefore, you cannot compare them. You cannot divide them. Instead, we are going to do the same thing that we did earlier. We will hold the limit process until we cook this function enough. How much should we cook? We need to prepare it. So to prepare, this is the preparation I'm going to have. Pay attention because this preparation is what we're going to have for each and every single problem in this section. We will look at the denominator. We will look at the largest x term in the denominator. Here in this case, it is x squared. Let's divide the numerator and the denominator by x squared. So when I do that here in the first example, I will show you all the steps. Eventually, you can get rid of some of them. Divide the top and the bottom by the largest x term in the denominator. So when you do that, now the next step is, now first of all, when you divide both the numerator and the denominator, essentially you did not change the mathematical form or the expression itself. So you're working with essentially the same function. So the limit that you're going to get for this one would be exactly the limit that you're going to get for this quantity. Now, let's try to do this separation here. This is a common denominator. So now if you divide throughout separately, you have 3x squared divided by x squared, 5x divided by x squared with a negative sign in front, 2 divided by x squared. So it would be split into 3 pieces, just like this, 3x squared divided by x squared. That becomes just 3x squared. X squared goes away with x squared, leaving just only 3. And then 5x divided by x squared, that would be 5 over x after the cancellation of one of the common factors, and then plus 2 over x squared. The whole thing is divided by, what's in the denominator? The similar computation, can you see? It is going to be 2 plus 1 over x minus 1 over x squared. Now when x goes to infinity, look at what would happen when x goes to positive infinity. If you can see this step, you can answer all of these steps. When x goes to infinity, what you have is exactly this. A finite number divided by a value that goes to infinity in the denominator. So that results 0. This one goes to 0. This one goes to 0. This one goes to 0. So at the top, what you have is 3 minus 0 plus 0 divided by, because 3 is right there. And in the denominator, you have 2 plus 0 minus 0. But zeros are nothing, right? There is no contribution from that. So the final answer that you're going to get in this scenario is, let me get a little more space for this. Don't need this one until we start working with that example, right? So now the final answer for this situation is 3 over 2. And there could be some algorithms. If you have seen similar computations, look at this. When you have the same power at the top and the bottom, one could say all you need to do is to compare the leading coefficients of each. But now there is no justification for that fact, right? So this is the justification. This is the work that you need to understand behind this kind of a problem. Now let's look at the next example. Since we know what's going to happen, let me do this. In this situation, I will directly do the computation and you can follow. Or why don't you take a moment? Try to do it yourself. Take a moment, pause this video and try to do it yourself. And when you have enough progress or when you have enough confusion, you can resume back and see how it's done. All right, I hope you gave it a try. Now, look at this. Here, I'm going to follow exactly the same recipe. X goes to negative infinity. What I'm going to do is to look at the largest power of x in the denominator, which is x square. Now divide the top and the bottom by that term. But now when I do that, I'm going to have the separation of each term. So 5x divided by x square, which is going to result 5 over x minus 3 over 3 here divided by x square, that would be 3 over x square. The whole thing is sitting at the top of this particular term divided by x square, that is going to be 1. X square divided by x square is 1. And then 1 over x minus 7 over x square. Now, by any chance, if you're still struggling to recognize this transformation from here to there, my recommendation is this. If you do not see it, this is a common trick that you're going to use mostly in calculus, because in calculus, in contrast to algebra, we do things in the opposite order so that we can simplify it in a meaningful way. If you do not understand what's in this direction, think about simplifying it backwards and see how they are connected. If you take the common denominator in the denominator, you can simplify. If you take the common denominator here, you can simplify. And then when you have denominators of denominators, you have two fractions, one on top of the other. Flip the denominator term and multiply, and you can get exactly this as a simplification. That is algebra. So if you keep doing that, what you're going to get is now this particular representation. And now the important part is all of these red highlighted terms are going to 0 when x is going to either infinity, positive or negative. It doesn't really matter, because x as a value increases without a bound and it's sitting in the denominator. So All of these are going to 0, 0. Our final answer will turn out the numerator has 0 because it's 0 minus 0, it's 0. In the denominator, it is 1, which is a perfect recipe because if you had 0 in the denominator, that would be a problem, but this is not, right? It's 0 at the top. So 0 divided by anything non-zero, it's going to be 0, and that is the value you're going to get. And one can qualitatively comment on this result. Look at this. You have a numerator in this scenario, in this function, where the numerator is linear, the largest power is just only x, and here the denominator has a larger power compared to the numerator. So when you compare these two components, you can see the denominator dominates this entire term when x increases. X squared goes to infinity faster than the term 5x. So that dominates, therefore the denominator has more power, it increases faster compared to the numerator. Therefore, the final result should be this. So you can think about it in that way qualitatively, but if somebody want to have a justification, and in fact in calculus you need to have these justifications, because when you use these concepts in later, like let's say when you are in calculus 2, differential equations, or any other required course in your major, or in the future somewhere when you see this computation, always the first thing, if you recall this as an algorithm, there's a possibility that you will get it mistaken sometimes, right? You recall it incorrectly. But when you have a method to justify it, it will remain with you forever. All right. So that is exactly why I would encourage you to have this connecting step. And then the next example. Now this is a situation, if you in terms of like the previous two examples, if you look at this particular scenario, you have a larger power at the top, and if I ask you to guess without doing anything, just guess what would happen. Take a moment to guess. You may be correct. Let's see. All right, so now I told you I'm going to go with one single uniform recipe for this entire computation. Look at the largest power of the denominator and divide that by that term, both the top and the bottom. So when I do that, when I divide the top by x squared, which is the largest power of the denominator, now I'm going to get negative 3x cubed divided by x squared. That cannot cancel x terms at the top completely. So that would be negative 3x plus 5x divided by x squared. That would be 5 over x plus 2 divided by x squared, that would be 2 over x squared. There is no further simplification that we can have in that. And when you do this in the numerator, you need to do the same in the denominator. Divide the denominator by x squared. So 2x squared divided by x squared, that would be 2, minus x divided by x squared, 1 over x, plus 7 divided by x squared, that would be x squared itself, 7 over x squared. Now look at each individual component. All of these fractions has the same characteristic. When x goes to infinity, positive infinity or negative infinity, it doesn't really matter. All of these are going towards just 0 and 0. And this part makes it non-zero in the denominator, which is nice. So let me put the denominator first. Over 2, and then I'm going to look at this. Wow, wait a minute, this seems an obstacle. Now when x goes to infinity, you have negative 3x. Essentially that should go to infinity. Since there's a negative sign in front, it's going to be negative infinity. So if you write it technically, this is what you're going to get, negative infinity over 2. Now look at this. it is not meaningful to talk about like dividing an infinity by half. But don't forget, infinity is not a number, it is a process, never ending process. So if you divide an infinity by 2, that's not going to change anything from that infinity. It's going to be just negative infinity yet. So our final answer in this scenario is negative infinity. Now let's recall what you thought about this problem, what kind of impression that you had about this problem in qualitative sense at the right at the beginning. Look at this. The numerator has a larger power, the denominator has less power, therefore the dominating power is concentrated around the numerator than the denominator. Therefore, wherever the numerator goes, that's exactly where this whole fraction would go due to this, right? When x goes to infinity. So that is exactly what we can think about in terms of computations. And now, based on these observations, if I ask you to write down horizontal asymptotes of these functions, it is going to be super straightforward. Look at this. Now, what we need is horizontal asymptotes only. To find horizontal asymptotes, all you need to do is to look at uh, limit at positive and negative infinity. Now look at this. Let's pretend you did that kind of a computation, but you know when you do that computation, you're going to get the comparison between the largest powers of the numerator and the denominator. So in this situation, that is nothing confusing. It's going to be y equals negative 7 thirds. The computation, if you're wondering what I did, my thought process to get to this answer is none other than the computation of limit at positive infinity or even at negative infinity of this function. I'm going to just do it in the same way, 3x cubed minus x plus 10. Now the work that I need in that occasion would be dividing both the numerator and the denominator by the largest x term in the denominator, which is x cubed in this occasion. So when you do that, you will get a perfect cancellation of all other terms except for these two leading coefficients at the end. That is what results as this. And then in this situation, you have less power of the denominator compared to the numerator. Therefore, you know the recipe. It's going to result y equals 0 after the computation. Again, I recommend you to have the limit computation. Limit x goes to either positive or negative infinity. It doesn't really matter. Look at the function and compute it, and that's what you're going to get. And this third scenario is where you have a larger power at the top and a smaller power at the bottom. Now, if you think about this, can you end up getting a possibility of a finite value just like these two cases? This is pretty much aligned with the last example that we worked with, right? So when you look at this example, you can see there is no finite limit resulting in this situation. So this is the situation where we do not have no horizontal asymptotes. So we do not have any horizontal asymptotes in this particular scenario. And that is, in other words, if you look at the graph, this is how it would look. That's a mystery in between, but we are looking at what's happening to the graph at the end, right? So the function is going towards an infinity or a negative infinity. In this situation, if you compute this limit, you will see it's going to be negative infinity in this end and positive infinity in the other end. So this is how the graph would look, but now that simply means it's not getting aligned with the vertical line segment, a horizontal line segment. Instead, it's skyrocketing to infinity or plummeting down to a negative infinity in each end. So that's exactly the situation where you do not have a horizontal asymptote at all. All right, so these graphical notions, by any chance, if you feel like these graphical conversations are a little bit like hard to grasp right away, don't worry, we will see them more in detail when it comes to applications of calculus later in a later module. At this point, you need to be familiar with the computational aspects of these limiting computations. And with this, we conclude limits at infinity and infinite limits, and um, have some practice on these computations, because these computations are extremely simple and pretty much like routine practice. All you need to do is to understand the very basics. All right, so I will meet you on the next lesson, further on limits.